The morning of November 15th, 1943, Commander Tameichi Hara stood on the bridge of the destroyer Shigure, watching the radar operator stare intently at the glowing Type 22 display. The officer's face showed concentration, then confusion, then something close to panic. "Contact," the operator reported. "Bearing 340, range 32,000 meters, 32 kilometers, just under 30 miles. The radar had detected the American task force approaching from the northwest, exactly as intelligence had predicted. This was good. This was what the new equipment was supposed to do. Hara checked his watch. The time was 01:15. They had perhaps 20 minutes before the enemy entered gun range, maybe less. The Americans were fast. "Sound battle stations," Hara ordered. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What commander? Hara didn't know. What no Japanese officer could have known at that moment was that the American ships had detected Shigure and her companion destroyers over an hour earlier. The American SG radar had painted Japanese ships on its screens at a range exceeding 65 kilometers, more than 40 miles. The Americans had been tracking, plotting, calculating firing solutions, and maneuvering into optimal attack position for the past 60 minutes, while Japanese destroyers sailed forward in complete ignorance. The Battle of Empress Augusta Bay was about to provide the Imperial Japanese Navy with an expensive education in the mathematics of radar warfare. The lesson would be repeated at Colombangara, at Vella La Vella, at Cape St. George. Each time, Japanese commanders would discover they were fighting with a fundamental disadvantage so severe it turned every tactical decision into a potential disaster. The gap wasn't 20 or 30 miles. The gap was time itself. Time to maneuver, time to prepare, time to choose. The Americans had it, the Japanese didn't. And by the time Japanese radar operators finally painted American ships on their scopes, the battle had already been lost. This is the story of how Japanese naval commanders discovered that technological superiority isn't measured in whether you have a capability. It's measured in whether your capability is good enough. And in the brutal mathematics of naval warfare in the Pacific, good enough meant the difference between hunting and being hunted. The world before radar. To understand why Japanese naval officers were so optimistic about their radar equipment in late 1943, you have to understand how dominant they had been in night combat before radar existed. The Imperial Japanese Navy had spent 2 decades perfecting the art of night surface warfare. Beginning in the 1920s, the Navy instituted brutal training regimens focused on night operations. Lookouts were selected for exceptional natural night vision, then trained relentlessly. They spent hours in darkened rooms, learning to distinguish shadows from solid objects. They practiced identifying ship silhouettes under minimal light conditions. They studied star positions and learned to estimate ranges using celestial references. The finest night binoculars in the world supported these lookouts. Japanese optical industry had produced magnification equipment with light-gathering capabilities no other navy could match. Under ideal conditions, trained Japanese lookouts could identify ship types at distances exceeding 8 miles in complete darkness. But lookouts were only part of the system. Japanese destroyer captains drilled constantly in night maneuvers. Formations practiced maintaining station in blackout conditions. Communications, protocols emphasized visual signals and radio silence. Torpedo crews trained to launch spreads by feel rather than sight. Most critically, Japanese destroyers carried the Taitajas, Type 93 torpedo, known to the Allies as the Long Lance. These oxygen-fueled weapons had ranges exceeding 40,000 meters. They ran faster and carried larger warheads than any torpedo in the American or British infantry. A Japanese destroyer could launch torpedoes from beyond visual range and expect hits. The combination was devastating. Lookouts detected enemy ships first. Destroyers maneuvered into attack position. Torpedoes launched from ranges American ships couldn't reach. By the time American lookouts spotted Japanese vessels, torpedoes were already in the water. This system worked brilliantly at the Battle of Savo Island in August 1942. Vice Admiral Gunichi Mikawa's 7 cruisers and 1 destroyer entered Iron Bottom Sound near Guadalcanal under cover of darkness. The American and Australian screening force included 2 radar-equipped destroyers specifically positioned to provide early warning. The radar destroyers saw nothing. Their SC radar sets had effective detection ranges between 4 and 10 miles. The Japanese formation passed more than 5 miles away. Beyond radar range, Japanese lookouts, meanwhile, spotted the American picket destroyer Blue at approximately 5 miles. The Japanese column held fire, guns trained. Blue turned away on her patrol track, completely unaware that 8 Japanese warships were passing close enough to engage with rifle fire. Minutes later, Japanese lookouts detected the American Southern Force cruisers at approximately 12,000 meters. They were silhouetted against the glow from a burning transport ship. Admiral Mikawa held fire while his ships launched torpedoes. Then Japanese float planes dropped flares, backlighting the American cruisers perfectly. The result was slaughter. In less than an hour, Mikawa's force sank 4 Allied cruisers and damaged 2 more. Japanese losses were negligible. A single inquiry board convened by Secretary of the Navy Frank Knox concluded that complete surprise had been achieved primarily because American radar had failed to provide adequate warning. Similar patterns repeated across the Solomon Islands campaign. At Tassafaronga in November 1942, 8 Japanese destroyers attempting a supply run encountered 5 American cruisers and 4 destroyers. The Americans had radar. The Japanese didn't. The Americans detected the Japanese first. They opened fire and sank 1 destroyer. Then Japanese destroyers launched 31 Type 93 torpedoes. They hit 4 American cruisers. 1 sank. 3 were severely damaged. The Americans had radar advantage, surprise advantage, numerical advantage in heavy units. They still lost the battle. Japanese commanders studied these actions and drew reasonable conclusions. Visual lookouts, when properly trained and equipped, could detect enemy ships at adequate ranges for night combat. Long lance torpedoes provided standoff attack capability. Aggressive tactics and superior night fighting skills could overcome temporary American advantages in radar technology. These conclusions were reinforced by Japanese radar development progress through 1942 and early 1943. By October 1942, experimental Type 22 radar sets were being installed on selected warships. The battleship Shigure received a pre-production model. The heavy cruiser Atago was fitted with an experimental set while undergoing repairs in November 1942. The Atago's radar proved its worth during the Battle of Empress Augusta Bay on November 2, 1943. 7 Japanese cruisers attempted to disrupt American landings at Bougainville. American aircraft attacked. In the confusion, Atago's radar crew used their equipment to navigate through hostile waters and avoid collision with friendly ships. The cruiser emerged unscathed. The success generated enthusiasm. By September 1944, Japanese shipyards were installing Type 22 radar on destroyers at an accelerating rate. The Type 22 was a 10-centimeter microwave set using cavity magnetron technology. It could detect aircraft groups at 35 kilometers, single aircraft at 17 kilometers, and large surface ships at 34.5 kilometers. 34.5 kilometers, approximately 30 miles. To Japanese naval officers in late 1943, this seemed adequate. Most night surface actions occurred at ranges under 20,000 meters. If radar could detect enemy ships at 30 kilometers, that provided 10 kilometers of warning and maneuvering time. Combined with superior Japanese night fighting tactics and long-lance torpedoes, radar-equipped destroyers should dominate night actions. The flaw in this reasoning was that Japanese officers were comparing their new capability against their old baseline, visual detection ranges of 8 to 10 miles. They had no framework for understanding that American radar wasn't just slightly better, it was twice as good. And in naval warfare, twice as good means you control when, where, and how the battle is fought. The technical reality. The American SG radar that became standard on destroyers and cruisers by early 1943 operated on similar principles to the Japanese Type 22. Both were microwave sets using S-band frequencies around 3 GHz. Both used cavity magnetron transmitters. Both displayed returns on circular plan position indicator scopes. But the similarities ended there. American SG radar had been developed through extensive cooperation between the MIT Radiation Laboratory, the Naval Research Laboratory, and Raytheon Corporation. British scientists had shared cavity magnetron technology through the Tizard mission in 1940. The first prototype was tested aboard the destroyer USS Semmes in May 1941. By April 1942, the heavy cruiser USS Augusta had an operational set installed. The SG radar had maximum detection ranges approaching 75,000 meters against large ships, over 40 miles. Even at more typical operating ranges, reliable detection of cruiser-sized targets occurred at 40 to 50,000 meters, 25 to 30 miles. Destroyer-sized targets could be detected at 30 to 40,000 meters. The difference wasn't marginal. It wasn't 10 or 15%. American radar could detect Japanese ships at ranges 50 to 100% greater than Japanese radar could detect American ships. This translated to time advantages measured in tens of minutes. Consider a hypothetical engagement between two destroyer forces approaching each other at a combined speed of 30 knots. If American destroyers detect Japanese ships at 40 miles and Japanese ships detect Americans at 30 miles, the Americans gain approximately 20 minutes of advance warning. 20 minutes to plot courses, calculate intercepts, position for optimal torpedo spreads, coordinate with supporting cruisers. 20 minutes changes everything. It's the difference between reacting to enemy movement and controlling it. It's the difference between launching torpedoes from prepared positions and launching in desperation while under fire. It's the difference between choosing the engagement range and accepting whatever range the enemy imposes. Japanese naval commanders had no way to know this performance gap existed. American radar capabilities were classified. Captured radar sets provided only partial information. Testing equipment ashore or in harbor didn't reveal operational ranges achievable at sea under combat conditions. More fundamentally, Japanese radar development had been hampered by factors Japanese officers couldn't overcome. The Navy's Electrical Research Department employed only 300 staff personnel by August 1943. This compared to thousands of engineers and technicians working on radar projects in the United States. Inter-service rivalry between Army and Navy meant each service developed separate radar systems that couldn't interrogate the other's aircraft. Quality control problems meant many produced radar tubes failed within 100 hours of operation. Resource shortages compounded these problems. Nickel needed for vacuum tube filaments was so scarce that coins containing nickel were purchased and melted down. Sophisticated electronic components had to be subcontracted to small companies with inadequate experience. The result was equipment that, when it worked, performed to specifications. But much of it didn't work reliably. Still, by late 1943, enough Japanese destroyers had operational radar that commanders believed they'd achieved technological parity with American forces. They were about to discover how wrong that assumption was. In December 1943, the destroyer Hamikaze returned to Yokosuka Naval Arsenal for routine maintenance. She had been the first Japanese destroyer to receive radar installation, fitted with a Type 22 set in late 1942. Her captain, Commander Shintaro Hashimoto, had more operational experience with shipborne radar than perhaps any other destroyer commander in the Imperial Navy. During the refit, naval technicians conducted calibration tests of Hamikaze's radar system. These tests involved measuring detection ranges against known targets at various distances. A target vessel would position itself at specific ranges, while Hamikaze's radar operators attempted detection. The results were recorded meticulously. Against a cruiser-sized target at 35 kilometers, detection was reliable. At 40 kilometers, the return signal became intermittent. Beyond 45 kilometers, detection was impossible. The tests confirmed what the technical specifications had promised. The Type 22 could detect large surface vessels at approximately 34 to 35 kilometers under ideal conditions. Commander Hashimoto reviewed these results with satisfaction. 35 kilometers provided adequate warning for night surface actions. His lookouts could still see targets at 8 to 10 miles. Radar extended that envelope by an additional 10 to 12 miles. This seemed sufficient. What Hashimoto didn't know was that American destroyer commanders conducting similar calibration tests were recording detection ranges nearly double what Hamikaze achieved. American captains expected to paint cruiser-sized targets at 60 to 70 kilometers. They trained their radar operators to identify contact classifications at 50 kilometers. They planned tactics assuming 40 to 50 minutes of tracking time before visual range. The performance gap wasn't theoretical. It was being demonstrated in combat repeatedly. But Japanese commanders who survived these actions attributed American advantages to other factors: superior communications, better fire control, numerical superiority, tactical mistakes on the Japanese side. The possibility that American radar was fundamentally more capable didn't occur to them because they had no reference point for such performance. Captain Tameichi Hara, commanding the destroyer Shigure, experienced this gap firsthand multiple times during 1943. Hara was one of the Imperial Navy's most skilled destroyer captains. He had survived the Battle of Java Sea, the Battle of the Philippine Sea, and numerous actions in the Solomons. He understood night combat better than almost anyone in the Japanese Navy. In July 1943, Shigure participated in the Battle of Kolombangara. The Japanese force consisted of 1 light cruiser and 5 destroyers, attempting to reinforce troops on Kolombangara Island. Intelligence indicated American forces might intercept, but Japanese commanders were confident. They had radar. Their formations included the newest destroyers with the best equipment. They had overwhelming torpedo firepower. The American force included 3 light cruisers and 10 destroyers, all equipped with SG radar. At approximately 0106 hours on July 13th, American radar operators detected the Japanese formation at ranges exceeding 35,000 meters, approximately 20 miles. Japanese radar operators detected nothing. Their equipment was operating normally. The Americans were simply beyond detection range. For 22 minutes, American ships tracked Japanese vessels, while Japanese crews remained unaware of their presence. American commanders plotted intercepts, calculated torpedo spreads, and maneuvered into optimal firing positions. They had time to organize their attack, coordinate between ships, and prepare damage control parties for expected combat. When Japanese radar finally detected American ships at approximately 30,000 meters, the Americans had already completed their tactical setup. What Japanese commanders perceived as a meeting engagement was actually an ambush. The Americans had controlled the battle's opening for 22 critical minutes. The engagement that followed saw the Japanese light cruiser Jintsu blown apart by concentrated gunfire in the opening minutes. American cruisers fired star shells that illuminated Japanese ships perfectly. Jintsu, flagship of the Japanese force, took devastating hits and sank rapidly. Rear Admiral Shunji Isaki died on his bridge. Japanese destroyers responded with massive torpedo launches. They fired 31 Type 93 torpedoes at the American formation. Multiple hits crippled the cruiser HMNZS Leander, damaged USS Honolulu and USS Street Louis, and sank the destroyer USS Gwyn. By traditional measures, the Japanese had won a tactical victory. They'd inflicted more damage than they received, but strategically, they'd failed. The American formation had achieved surprise, controlled the engagement's opening phase, and destroyed the Japanese flagship in the first minutes of combat. The reinforcement mission was disrupted. Japanese destroyers were forced to scatter and withdraw. The Americans retained control of the waters around Kolombangara. Captain Hara's after-action report noted that American forces appeared to have detected Japanese ships earlier than Japanese radar detected Americans. He attributed this to possible altitude advantages. American ships might have had their radar antennas mounted higher, extending horizon distance. He noted that American star shells seemed prepared in advance, suggesting foreknowledge of Japanese positions. But he didn't conclude that American radar had fundamentally superior range. The pattern repeated at the Battle of Vella La Vella on October 6, 1943. 9 Japanese destroyers were evacuating troops from Vella La Vella Island when they encountered 6 American destroyers. Both sides had radar. Both detected each other at, roughly similar times, between 15 and 20,000 meters. The resulting action was chaotic, fought at close range with both sides taking casualties. Japanese commanders noted with satisfaction that radar hadn't provided Americans with significant advantage in this engagement. What they didn't realize was that American commanders had chosen to close to shorter ranges, deliberately. The American force had detected Japanese ships much earlier, but had opted to maneuver for close-range torpedo attacks rather than engaging at maximum range. The Japanese perception was that radar ranges were roughly equivalent. The reality was that Americans had controlled the engagement geometry from initial detection onward. By late 1943, Japanese destroyer captains had developed a collective understanding of radar's capabilities based on their combat experience. They believed detection ranges were similar between American and Japanese equipment, with perhaps slight American advantages in some conditions. They believed radar provided useful early warning, but didn't fundamentally change night combat tactics. They believed their superior training, better torpedoes, and aggressive doctrine could still produce victories. These beliefs were about to be shattered. The climax, the battle off Cape Street. George. The night of November 25, 1943, marked the turning point where Japanese confidence in their radar-equipped destroyers collided with devastating reality. 5 Japanese destroyers departed Rabaul on a supply and troop evacuation run to Buka Island. The force consisted of 3 destroyers carrying supplies and troops, Amagiri, Uzuki, and Yugiri, screened by 2 combat destroyers, Onami and Makinami. All 5 ships had radar. The 2 screening destroyers, Onami and Makinami, had recently installed Type 22 sets and Type 13 air search radar. They represented the Imperial Navy's most modern radar-equipped destroyers. Captain Kiyoshi Kagawa commanded the screening force from Onami. He was an experienced officer who understood both traditional night-fighting tactics and the new radar capabilities. His orders were to protect the transport destroyers, detect any American interference, and use his radar to maintain situational awareness throughout the mission. American intelligence knew the Japanese were coming. Coast watchers had reported the departure from Rabaul. Captain Arleigh Burke commanded Destroyer Squadron 23, 5 Fletcher-class destroyers, all equipped with SG radar. Burke was aggressive, confident, and determined to demonstrate that American destroyers could dominate Japanese forces in night combat. Burke positioned his ships to intercept the Japanese return route from Buka. His plan was simple: use radar to detect the Japanese force at maximum range, maneuver for optimal attack position, and launch a coordinated torpedo and gunfire attack before the Japanese could effectively respond. He had drilled his squadron relentlessly. His radar operators were among the best in the Pacific Fleet. At approximately 0141 hours on November 25th, American radar operators detected the Japanese formation. Range, 46,000 meters, over 28 miles. The Japanese were returning from Buka, traveling at 24 knots, formation lights extinguished, maintaining strict radio discipline. Burke's radar operators tracked the contacts, identifying 5 ships in 2 groups. The lead group of 3 ships appeared to be cargo vessels or transports. 7. They were maintaining steady course and speed. The trailing group of 2 ships seemed to be combat escorts, maneuvering slightly as they protected the formation's rear. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Burke made his decision quickly. He would split his force. 3 destroyers under his direct command would attack the trailing combat escorts. 2 destroyers under Commander Bernard Austin would pursue and engage the transport group. The goal was to destroy all 5 Japanese ships before they could scatter or counterattack effectively. For 45 minutes, Burke's destroyers tracked the Japanese formation while remaining undetected. Radar operators called ranges continuously: 40,000 meters, 38,000, 35,000. Fire control computers calculated intercepts. Torpedo solution data flowed to weapons officers. Crews manned battle stations. Damage control parties prepared, all while Japanese destroyers sailed onward, completely unaware. At 30,000 meters, Japanese radar on Onami finally detected contacts astern. Range, approximately 29 kilometers. The Americans had closed to within detection distance. Captain Kagawa faced a crisis that unfolded in seconds. Unknown contacts were approaching from astern. His first thought was that American destroyers had somehow gotten behind his formation. But how? When had they detected the Japanese force? How long had they been tracking? Kagawa ordered flank speed and began turning Onami to face the threat. He signaled Makinami to follow. The 2 screening destroyers increased speed to 30 knots and swung around to protect the transport group, which continued toward Rabaul. But the Americans had 45 minutes to prepare. Burke's 3 destroyers were already in optimal attack position. They'd plotted Japanese courses, calculated intercepts, and positioned themselves between the Japanese combat destroyers and the transport group. When the Japanese turned to face them, the Americans were ready. At 0241 hours, Burke ordered his destroyers to open fire. The range was approximately 12,000 meters. American 5-inch guns launched star shells that burst above Onami and Makinami, illuminating both destroyers in harsh white light. Immediately, high explosive rounds followed. Onami took hits almost immediately. American gunfire was devastatingly accurate. Fire control radar had tracked the Japanese ships for 45 minutes. Gun directors had precise range, bearing, and course data. The first salvos straddled Onami perfectly. Subsequent salvos walked onto the target with methodical precision. Captain Kagawa tried to maneuver, tried to bring his torpedoes to bear, tried to close range where his ship's weapons could be effective. But American destroyers maintained separation, kept the range open, and continued firing from positions where their radar-directed gunfire was most effective. They weren't fighting the close-range, confused melee that Japanese doctrine expected. They were fighting a methodical execution from carefully controlled range. Onami was hit repeatedly. Fires broke out amidships and aft. The steering mechanism was damaged. Speed dropped. Still, Kagawa tried to fight back. His gun crews returned fire toward the muzzle flashes they could see. But without precise range data, without clear targets, their fire was ineffective. At 0256 hours, 15 minutes after the action began, Onami suffered a catastrophic hit that penetrated her magazines. The explosion tore the destroyer apart. She sank in minutes. Captain Kagawa died with his ship. There were no survivors. Makinami attempted to screen Onami and launch torpedoes at the American formation. She fired 8 Type 93 torpedoes toward the American destroyers. All missed. The Americans had maintained ranges beyond 20,000 meters, outside the effective envelope for torpedo attacks launched without precise target data. American destroyers shifted fire to Makinami. The pattern repeated. Starshells illuminated the target. High explosive rounds followed. Makinami was hit repeatedly across her length. Fires erupted. Her forward gun turrets were destroyed. She began to list. At 0328 hours, Makinami was dead in the water, burning from bow to stern. American destroyers ceased fire and moved to engage the transport group. Makinami would sink later that morning. Of her crew of 240, only 37 survived. Meanwhile, Commander Austin's 2 destroyers pursued the 3 transport destroyers. Using radar, they tracked the Japanese ships through the darkness. At 0306 hours, Austin's destroyers closed to torpedo range and launched. Multiple torpedoes hit Yugiri. She exploded and sank almost immediately. Amagiri and Uzuki scattered. They managed to escape by turning directly toward the American destroyers and passing at close range, where American radar had difficulty tracking low, fast-moving targets close aboard. Both Japanese destroyers survived, but they'd abandoned their cargoes, jettisoned their troops' equipment, and fled at maximum speed. The mission was a complete failure. The cost of understanding the battle off Cape Street, George ended Japanese destroyer dominance in night combat. For the first time, American destroyers had comprehensively defeated a Japanese destroyer force in a night surface action. The margin of victory wasn't close. 2 Japanese destroyers sunk, 1 severely damaged, 3 forced to flee. American casualties, minor damage to 1 destroyer from near misses. The battle reports filed by surviving Japanese officers revealed a growing awareness of the technological gap. The commander of Amagiri noted that American forces appeared to have detected the Japanese formation at ranges exceeding 35 kilometers, well beyond the capability of Japanese Type 22 radar. He noted that Americans maintained separation throughout the engagement, controlling the battle at ranges where Japanese weapons were less effective. Other surviving officers reported similar observations. American star shells were fired with precision that suggested prearranged targeting data. American maneuvers seemed coordinated in ways that implied shared situational awareness beyond what visual signaling could provide. American gunfire was accurate immediately, without the ranging salvos typical of visual fire control. These reports reached the Naval General Staff in Tokyo by early December 1943. They were analyzed by technical officers who began, for the first time, to seriously consider the possibility that American radar capabilities significantly exceeded Japanese equipment. In January 1944, the Navy Ministry ordered comprehensive testing of captured American radar equipment. Several SG radar sets had been recovered from downed aircraft and sunken ships. These sets were examined by Japanese electronics engineers, who discovered to their shock that American equipment achieved detection ranges 40 to 60% greater than comparable Japanese sets using similar frequencies and power levels. The difference came down to sophisticated engineering details that Japanese industry couldn't easily replicate. American radar used superior antenna designs that focused transmitted energy more efficiently. Receiver circuits incorporated better noise filtering that allowed detection of weaker return signals. Manufacturing quality control ensured vacuum tubes operated reliably within specifications. Integration with fire control computers allowed effective use of radar data at longer ranges. Japanese engineers could understand these advantages intellectually. They could measure them. They could document them in technical reports. What they couldn't do was fix them. The problems were systemic. Inadequate industrial capacity, insufficient raw materials, limited engineering workforce, quality control failures across the entire electronics manufacturing sector. By mid-1944, Japanese destroyers were receiving upgraded Type 22 Modification 2 radar sets with improved fire control capability. But detection ranges remained fundamentally limited to 30 to 35 kilometers against large surface targets. Meanwhile, American destroyers were receiving improved SG-1 radar with enhanced reliability and slightly extended ranges. The gap wasn't closing. If anything, it was widening. Japanese destroyer captains adapted their tactics as best they could. They emphasized aggressive closing maneuvers to get inside American radar-directed gun ranges quickly. They relied increasingly on submarine and aircraft reconnaissance to provide advance warning of American force movements. They operated in waters close to land where terrain clutter degraded American radar effectiveness. These adaptations helped, but they were defensive measures, attempts to mitigate a fundamental disadvantage rather than overcome it. Japanese destroyers were no longer hunting American forces at night. They were attempting to survive engagements they couldn't avoid. The statistics tell the story. In 1942, Japanese destroyers inflicted devastating losses on Allied forces in night actions while suffering relatively modest casualties themselves. In 1943, losses began to even out as American radar improved and American crews gained experience. In 1944, the ratio reversed. American destroyers dominated night actions, sinking Japanese destroyers at rates 3-1 or higher. By late 1944, Japanese destroyer strength had been gutted. Of the 126 destroyers the Imperial Navy operated at the start of the Pacific War, only 38 remained operational. The Kajo class, which had fought so effectively in early campaigns, was nearly extinct. Of 19 ships in the class, only 5 survived past mid-1944. The Yugumo class, which entered service in 1941 as Japan's most modern destroyers, lost 17 of 20 ships by the war's end. These losses couldn't be replaced. Japanese shipyards built approximately 70 destroyers during the Pacific War. American shipyards built over 300, but numbers alone don't capture the magnitude of the disaster. Japanese destroyers in 1944 and 45 were forced to operate in ways that negated their design advantages. Ships built for aggressive night torpedo attacks were reduced to convoy escort duty, running supply missions to isolated garrisons, and attempting to evacuate troops from losing positions. The radar gap was only one factor in this decline. American submarines devastated Japanese shipping, forcing destroyers into anti-submarine warfare roles they weren't optimized for. American carrier aviation achieved air superiority, making daylight operations suicidal. American industrial production created numerical advantages that overwhelmed Japanese forces regardless of tactical skill. But radar mattered. It mattered because night surface combat had been the one domain where Japanese destroyers held clear superiority. Superior optics, better training, more effective torpedoes, aggressive doctrine. These advantages had produced victories when American advantages in other areas were negated by darkness. Radar gave Americans the ability to fight at night with the same precision they achieved in daylight. Once that happened, Japanese destroyer forces could no longer win. Captain Tameichi Hara survived the war as one of the few destroyer commanders to serve from Pearl Harbor to the Japanese surrender. His ship, Shigure, survived longer than almost any other Japanese destroyer, finally sinking in January 1945 after being torpedoed by the submarine USS Blackfin. In post-war interviews, Hara spoke candidly about the radar gap and its impact. He noted that by mid-1944, Japanese destroyer captains knew they were operating at a severe disadvantage in night combat. They knew American radar could detect them before Japanese radar detected Americans. They knew American ships would have time to prepare, to maneuver, to coordinate attacks while Japanese ships were still sailing in ignorance. Yet they continued fighting because they had no choice. Orders came down. Missions had to be run. Troops needed supplies. Garrisons had to be evacuated. Retreating forces required protection. The destroyers that remained operational were committed to actions where their disadvantages were understood but accepted because the missions were deemed necessary. Hara described this as fighting with one eye closed and one hand tied. Japanese destroyers still had formidable weapons. The long-lance torpedoes were still deadly. The gun crews were still skilled. The ships could still maneuver effectively, but they were fighting from positions of disadvantage established before combat began, disadvantage created by technological gaps they couldn't overcome. The experience of the destroyer Yukikaze illustrates both the limitations Japanese ships faced and the skill with which their crews still fought. Yukikaze participated in nearly every major naval action of the Pacific War. She fought at the Java Sea, Midway, the Philippine Sea, Leyte Gulf, and numerous actions in the Solomons. She survived the entire war, one of the few destroyers to do so. Yukikaze survived not through superior technology, but through exceptional seamanship, aggressive tactics, and considerable luck. Her captain, Commander Terauchi Masamichi, understood the radar disadvantage and compensated by using terrain, weather, and smoke to mask his ship's approach. He trained his crews to fight at close range where American radar advantages were minimized. He emphasized rapid torpedo launches followed by immediate disengagement before American gunfire could achieve bracketing. These tactics worked often enough to keep Yukikaze operational, but they were the tactics of the hunted, not the hunter. Japanese destroyers had gone from dominating night combat to surviving it. The broader strategic implications extended beyond individual ship survival. The radar gap affected Japanese naval operations at every level. Surface task forces couldn't operate at night without accepting that American forces would detect them first, track them continuously, and engage from positions of advantage. This forced Japanese naval operations into daylight hours, where American carrier aviation could devastate them. Or it forced operations into narrow waters close to shore, where American submarines waited. The shrinking operational flexibility constrained Japanese strategic options progressively throughout 1944. Each major operation saw Japanese forces attempting to maneuver under conditions where American forces held information advantage. At the Battle of the Philippine Sea in June 1944, American carriers and battleships used radar to track Japanese forces throughout the night, maintaining contact while remaining beyond Japanese detection range. American commanders knew exactly where Japanese ships were at all times. Japanese commanders operated on outdated intelligence and guesswork. At the Battle of Leyte Gulf in October 1944, radar allowed American destroyer groups to ambush Japanese surface forces repeatedly. During the battle off Samar, American destroyers and destroyer escorts used radar to launch torpedo attacks while laying smoke screens that blocked Japanese visual observation. The Japanese battleships and cruisers had massive firepower advantages but couldn't bring that firepower to bear effectively against targets they could barely see, while American radar tracked them precisely. The technological disparity affected morale as well as tactics. Japanese destroyer crews knew they were sailing into combat with equipment inferior to what their opponents fielded. They knew their lookouts, no matter how skilled, couldn't match radar for consistent detection at long range. They knew their tactics, no matter how aggressive, couldn't overcome information, disadvantages measured in tens of minutes of warning time. This knowledge bred caution, even among the most aggressive commanders. Ships that might have pressed attacks in 1942 and 43 withdrew in 1944, knowing that pushing forward meant sailing deeper into radar coverage, where American forces would have every advantage. The psychological impact of fighting from disadvantage accumulated over months of combat until even elite destroyer divisions were shadows of their former effectiveness. Post-war analysis by American naval intelligence concluded that Japanese radar development had been hampered by four critical factors. First, late recognition of radar's importance meant Japanese programs started years behind American and British efforts. Second, inter-service rivalry between Army and Navy meant duplication of effort and failure to share technological advances. Third, inadequate industrial capacity and raw material shortages limited production of high-quality components. Fourth, quality control failures meant equipment that worked in testing often failed under operational conditions. None of these problems were easily solvable. They were embedded in Japan's industrial base, military culture, and resource constraints. Even if Japanese engineers had fully understood American radar capabilities by mid-1943, they lacked the means to close the gap quickly. Manufacturing cavity magnetrons with American precision required machine tools Japan didn't have. Producing reliable vacuum tubes required quality control processes Japanese industry couldn't implement at scale. Developing sophisticated fire control integration required engineering man-hours Japanese radar programs couldn't allocate. The result was a widening gap that Japanese forces observed, measured, and understood but couldn't fix. By 1945, American destroyers operated with such confidence in their radar superiority that night actions were sought, rather than avoided. American doctrine emphasized radar-directed approaches, coordinated torpedo attacks launched from precise positions, and gunfire engagements conducted at ranges where American fire control radar provided overwhelming accuracy advantages. Japanese survivors of late-war destroyer actions described these engagements as nightmarish. American star shells would suddenly illuminate Japanese ships that had no idea Americans were nearby. Radar-directed gunfire would immediately follow with accuracy that seemed impossible in darkness. Japanese attempts to close range and launch torpedoes would be countered by American maneuvers that maintained separation, while continuing to pound Japanese ships with gunfire. The night of April 6th and 7th, 1945, saw one of the last major Japanese destroyer actions. 8 destroyers escorted the battleship Yamato on a one-way suicide mission to Okinawa. American submarines detected the force's departure. American carrier aircraft shadowed the formation throughout its approach. When American planes attacked on the afternoon of April 7th, they did so with complete knowledge of Japanese formation, course, and speed. Radar-equipped aircraft coordinated their attacks with precision that would have been impossible relying on visual navigation. Yamato was sunk. 4 destroyers were sunk with her. Not a single ship reached Okinawa. The mission achieved nothing except demonstrating that Japanese surface forces could no longer operate within range of American air power, which itself was directed by radar systems that allowed coordination impossible for Japanese forces. The final accounting was brutal. The Imperial Japanese Navy began the Pacific War with destroyers that were, ship for ship, among the best in the world. They were fast, heavily armed, equipped with the best torpedoes afloat, and crewed by highly trained sailors. They dominated night combat through late 1942. By war's end, they'd been systematically destroyed. Survival rates for destroyer crews were appalling. Of the approximately 30,000 Japanese sailors who served on destroyers during the Pacific War, fewer than 8,000 survived to see Japan's surrender. The radar gap wasn't the only reason for this catastrophe, but it was a critical reason. It transformed night combat from a domain where Japanese destroyers held advantages to a domain where American forces could leverage superior numbers, superior firepower, and superior coordination. It made every night action a calculated risk for Japanese forces rather than an opportunity to inflict disproportionate casualties. And it demonstrated a harsh truth about modern warfare. Technological advantages don't require overwhelming superiority to be decisive. American radar wasn't twice as good as Japanese radar. It was 50% better in detection range, but 50% better meant 20 to 30 minutes more warning time. And 20 minutes was enough to transform naval combat from a test of seamanship and courage to a test of who controlled information. Japanese destroyer captains who tested captured radar sets in late 1943 discovered that 30-mile detection range was too late. By the time their equipment painted American ships on radar screens, the Americans had already been tracking them for half an hour. The battle geometry was already established. American ships were already positioned. American weapons were already aimed. What Japanese captains perceived as initial contact was actually the moment Americans chose to reveal themselves. The real initial contact had occurred miles earlier and minutes before, when American radar operators had called out first detection. The Japanese were fighting battles that had already been partially lost before they knew the battles had begun. This is the cost of technological inferiority in modern warfare. Not that your weapons don't work. They work. Not that your tactics are wrong. They might be sound, but that your opponent sees you before you see him, tracks you before you track him, prepares before you prepare, and by the time you realize you're in a fight, you're already losing. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.